Hello, everyone, and I hope you're all doing well. Thank you, Alex and Sean, for the invitation to speak. And thank you, everyone else, for zooming in. It's a great pleasure to have the opportunity to share these results with you. And what we are going to be doing is to be talking about Laplace eigenfunctions, although I'm going to explain later that all of this can be translated to more general operators. The goal of this talk is to discuss how eigenfunctions concentrate as measured by their LP norms. Everything I'll discuss today is joint work with Jeff Galkowski, and it builds on work we've been doing for a couple of years now. So there is a good chance that some of you may have seen part of this talk. And if this is the case, you should know that you haven't seen it all, as it's the first time that I'm talking about LP norms.
Sorry, Yaiza, I muted you by mistake. Can you
unmute yourself? Do you hear me now?
Yes, sorry.
So you heard all the way up until what?
More general operator than Laplacian, and that's it.
Okay, so the goal of this talk is to discuss how eigenfunctions concentrate as measured by their LP norms. And everything I'll discuss today is joint work with Jeff Galkowski. And it builds on work we've been doing for a couple of years now. We developed what we call geodesic beam techniques. And this is a set of tools that allows us to understand eigenfunction concentration on a manifold by understanding how the eigenfunctions localize in phase space. So I'll explain what I mean by this in more detail soon, but now I'm gonna start the talk focusing on the end goal, which is LP norms. Can you confirm that you hear me just fine?
Yes.
Yes, we hear you well.
Good, excellent. Okay, so LP norms, here we go. We are gonna work on a compact Riemannian manifold. We are gonna assume it's smooth, that it has no boundary, and throughout the talk, the dimension of the manifold is gonna be this n. It's gonna show up in all the estimates I'm gonna be presenting. Now, we are gonna work with Laplace eigenfunctions. The convention that we will use is that the eigenvalues are lambda squared, not just lambda. So just keep this in mind. And unless I say otherwise, the eigenfunctions are going to be normalized so that their total L2 mass is equal to 1. Now, when it comes to L infinity norms, the result is that eigenvalues, eigenfunctions, they cannot grow faster than lambda to the n minus 1 over 2, again, n being the dimension of the manifold. This result is due to Levitan and Abakhmovich, and in full generality due to Hormander. Throughout the talk, I will likely refer this to as either the universal bound or Hormander's bound. And if you want to move from L infinity norms to general LP norms, we have Zog's bounds, which say that the LP mass of an eigenfunction is bounded now by lambda to the n minus 1 over 2 plus n over p. So this only works when p is bigger than this number over here. This is what we call the critical exponent. And of course, when p is equal to infinity, then this bound becomes the one that we have upstairs. Now, what the goal for this talk is to obtain quantitative improvements that should work on most manifolds. So we want improvements on these bounds. And in general, we are gonna make assumptions that are not gonna be global on the geometry of the manifold in order to get these improvements. But now it's a good moment to mention that since what we want is improvements on the bounds, one example of eigenfunctions that saturate these bounds are the zonal harmonics on the sphere. So if this is the n sphere, yeah, the zonal harmonics are just eigenfunctions that peak both at the north and south pole. So this is the plot of the absolute value of the eigenfunctions. And the way in which they peak is that the height of this peak is lambda to the n minus 1 over 2. So really at the north and south pole, these eigenfunctions are saturating the L infinity norm. And actually, these zonal harmonics, they also saturate the LP norms as long as you remain above the critical exponent. What we will see as the talk evolves is that the points on a sphere, they have this very particular property, and that is that they are maximally self-conjugate. This means that if I start here at the North Pole, no matter in which direction I move away from the North Pole, geodesics are gonna move along the sphere and come back to the point, and they are gonna close when they return. And the fact that this is going to happen in every possible direction that you may take once you start moving on the sphere, it's exactly what's going to make these bounds saturate. And I'm going to try to explain that as soon as you step off this realm, then you're going to be able to improve on these bounds. So before explaining how to improve on these bounds, what I want to do is to explain what the geodesic beam techniques that we've been developing are about. So in this slide, what I'm doing is exactly that. We are going to fix a point X on the manifold, and we are going to decompose our eigenfunction near the point X. And this is important. This is not a global decomposition for the eigenfunction. This only works locally. And the way in which we are going to decompose the eigenfunction is as a superposition of what we call geodesic beams. So each of these elements is what we call a geodesic beam. And the way in which we build them is as follows. So you have this point here, X, and this is a picture in Sx star M if you want. And then what you're gonna do is you're gonna give yourself a radius function. This radius r of lambda is gonna go to 0, like lambda to the minus delta. Delta needs to be strictly smaller than 1/2, but for the purposes of the talk, you can think that delta is exactly equal to 1/2. And what we are gonna do is you have the co-sphere fiber at X, and we are going to cover the co-sphere fiber using balls of radius r lambda. And then what we are going to do with these balls is we are going to turn on the geodesic flow, and we are going to flow them out, and we are going to turn them into tubes. So each of these blue rectangles here that you see is supposed to represent a tube. And what this is localizing the function in phase space to the tube. So again, these tubes are living in phase space. And the idea, I'm going to explain exactly how we do this, but the idea is going to be to control the value of the function at the point X in terms of how each of these tubes is going to evolve under the action of the geodesic flow. So let me explain what I mean by localizing the functions. What is it that each of these geodesic beams actually is? I'm going to build an operator. This is going to be for each tube that we denote Tj. We build this operator chi Tj. And the way in which we build it is we are going to grab a function in phase space whose support is inside the tube, and we are going to quantize it. So what this operator is going to do is micro-localize my eigenfunction to the tube Tj. If you're not familiar with what that means, you should think that in each of these beams, what we are doing is we are localizing the function in position near the point X and in frequency to the tube. So you should think that the Fourier transform of the eigenfunction has support with frequencies inside these tubes.
So H is 1/λ?
Yeah, so I really try to avoid using H, but here I felt very awkward about writing up 1/λ. So I decided to leave it like that, but yes, it's 1/λ. And now the way in which we are going to build these beams is by asking them to locally solve our eigenvalue problem. So we are going to ask them to be local solutions, like they should behave locally like an eigenfunction of eigenvalue lambda squared. And the way in which, and the reason, I mean, we heavily use this, and this is what imposes that our tubes should be centered around geodesics. So let me explain that for a second. So you know that the eigenfunction is that phi lambda is an eigenfunction of this operator. So basically what we want to do is we want to be able to commute these two operators together. So we are asking for the commutator to be roughly 0 near the point. This is again all local. And at least at the level of principal symbols, what this implies is that if you hit your cutoff function in phase space with the Hamiltonian flow, the geodesic flow, you should get a 0. So this means that your cutoff function has to be invariant under the geodesic flow. And this is why the tubes need to be centered around geodesics for us. We need each of these beams to behave locally like a solution for our problem. And the general idea is that we are fixing the point x, and we want to control the value of the function at the point x in terms of how each of these beams is going to evolve under the geodesic flow. So this is the general idea behind the techniques. Now, what I want to give you is a sense of how is it that one can think of an eigenfunction as a superposition of beams. And I'm going to do that on the sphere. The sphere is quite particular because on the sphere one can build beams that are actually globally defined. They are called highest weight spherical harmonics on the sphere. So this is the plot of the absolute value of one of them. And what they do is they concentrate along a great circle, and they concentrate on a tube along the great circle. So this is your tube here, or your tube here. And the width of the tube is exactly this r of lambda, which for our purposes, and actually on the sphere this is actually true, r of lambda is equal to lambda to the minus a half. Now, the height of these functions along this band goes all the way up to lambda to the 1/4. So, and again, for the sphere, these are actually eigenfunctions that are globally defined. But in general, for us, they are only going to be defined locally. So you're going to pick a piece of your geodesic, and that's where you are going to, that's where the beam takes place. Now, just keep in mind that again, this is the plot of the absolute value of the function. So the eigenfunction actually is oscillating like this along the equator. So here, for example, you have the profile along the geodesic beam. Again, the height of each of these waves is like lambda to the 1/4, and they occur every 1/λ units. The goal for us is going to be to try to superpose many geodesic beams so that we can actually create the behavior that a zonal harmonic has at, say, the South Pole. So here we have the South Pole, and remember the zonal harmonic was peaking at the South Pole like lambda to the 1/2. So here, this is the picture for the two sphere. So Hormander's bound is like lambda to the n-1/2. So here, lambda to the 1/2 is the behavior that the zonal harmonic has at the North and South Pole. And what we want to do is to consider a superposition of beams that will recreate this peak. So we are going to put the beams going through this point here. And what happens is that if you put a single beam, say along that great circle, that's this single beam over here, then the maximum L-infinity norm that you can pick is lambda to the 1/4, because that's the height of your beam. This is of course not enough, because instead of lambda to the 1/4, what we want is a lambda to the 1/2. So a single beam is not gonna reproduce what a zonal harmonic does. So you start adding beams through this point. So now instead of considering just this great circle, you consider this one, say, in addition to it. And now what happens is that when you consider the superposition of the two beams, the height of the peak, of course, duplicates. And now the only thing that you have to keep in mind as you keep adding beams to this picture is that you have to keep track of the L2 norms, because this bound here that I'm writing works when the L2 norm is equal to 1. And if we add two beams together, the L2 norm, they are orthogonal to each other. So the L2 norm now change, and it's square root 2. And then what you do is you just keep adding beams through the point. And what you quickly realize is that what you have to do is to add as many beams as they can possibly fit in order to recreate this peak at the South Pole. And if you try to answer that question and try to understand how many beams you can fit in that circle, you need to remember that the width of the band of a single beam was like lambda to the -1/2. So you can fit lambda to the 1/2 beams on this circle while still keeping them orthogonal to each other. So you fit lambda to the 1/2 beams, the L2 norm grew like square root of lambda to the 1/2. So when you normalize your problem, these two terms go away, and now the L infinity norm is growing like lambda to the 1/2, which was your goal. So this is actually how one reproduces the behavior of a zonal harmonic at the south pole, say. You have to put the maximum possible number of beams through a point, all of them with this mass. And this is gonna keep showing up in the picture, but hopefully you get the idea that one can actually get other behaviors for eigenfunctions if you put fewer tubes, and also if the masses in each of the tubes change. So now what I'm gonna do in the next slide is to explain how is it that one can use tubes to control the value of a function at a point. And so what we are going to do is we are going to fix a point on the manifold. Here, lambda is just a function that's going to go to 0. So we are going to be studying L infinity norms in a ball of radius R lambda around X. And what we are going to need is to be able to split your family of tubes. This is the entire family of tubes into two groups. So we are going to have the bad tubes and the good tubes. Bad tubes throughout the talk are going to be orange, good tubes are going to be green. And what good means is that if you look at your collection of good tubes, then this collection needs to be non-self-looping for logarithmic times. So here in this picture, you look at all the green tubes, and now you flow them out using the geodesic flow for time log lambda. And what you're requiring is that these flows should not loop back to themselves for logarithmic time. In the picture, this tube here is orange because infinite time is looping back. If you are somehow able, because of the geometry of your problem, to split the tubes into these two groups, then what you can prove is that you can control the L infinity mass of your eigenfunction at the point X, so the value of the function at the point X, by the following. And I'm going to parse every part of this upper bound for you. Here, what we have, this is Hormander's bound, a constant that depends only on n times lambda to the n minus 1/2. Here you have the radius of the tube. And this is the number of bad tubes, the number of good tubes. It's divided by the time for which the good tubes are non-self-looping. And this is the mass of the L2 function. So that you have a better idea of what this bound represents, remember that what we were doing was to build the tubes in the cosphere fiber at X. So we were building balls of radius R lambda, and we were propagating them to form the tubes.
Sorry, Yaiza, I have one question. What is R of lambda?
Yeah, oh, R of lambda. R of lambda for us, you may think of it, so for our work, R of lambda is lambda to the minus delta, delta being strictly smaller than 1/2. But throughout the talk, what you can think is that R of lambda is exactly like lambda to the 1/2. That's the picture you should have.
So this
just
is
like the highest
radius
spherical harmonics do on the sphere. The
this
truth
is
is
like
that
the radius of the
sorry,
minus
what?
minus 1/2.
minus.
Yes, minus 1/2.
So this is the width. This is the width. This is the radius
so
of
each
the
of the
tube.
beams, you should think of it as a tube, and the radius of the tube is shrinking. So again, so you cover the cosphere fiber using balls of radius R of lambda. These balls are shrinking with lambda. And then you propagate these balls using the geodesic flow, but for a very short time. So you have these tiny tubes with which you're covering the cosphere fiber at X. And these tubes, as lambda goes to infinity, they are going to shrink around the geodesic. And this is
Can I also ask a question, please?
Yeah.
It's Alex. What does it mean to be non-self-looping? Is it the same as the geodesic not being closed?
No, for a geodesic to be closed is stronger. What we are asking is that you look at this entire green family of tubes, you flow it using the geodesic flow, and it cannot come back to overlap with itself for a time smaller than log lambda. But you don't ask that it overlaps exactly the same.
Yeah,
like
okay.
It's just looping, not closed geodesic loops. Okay?
Thank you.
Okay. So because you're covering this cold sphere fiber at X, and these balls have their heads in the cold sphere fiber, then the volume of each of these tubes is R of lambda to the power of n minus 1. So what you're seeing here is the volume of a single tube, the square root of the volume of a single tube. So what you can do is to combine this radius with the number of balls and think of this estimate as an estimate on the value of the function at the point X in terms of the volumes of the set of bad tubes plus the volume of the set of good tubes. And of course, what you want to do is somehow use the geometry of your problem in so that this volume should be a remainder when you compare it against this. So the volume of the set of bad tubes should be smaller than 1 over log lambda. And what I want to explain before actually giving you a geometric setup where you can use this is where is it that this result comes from. So we have an estimate, our main estimate, that controls the value of a function at a point X in terms of the L2 masses of each of these beams that are departing from X. So this term in front of the sum is exactly the same as what we had here. The only thing that changed is that instead of now talking about numbers of good and bad tubes, the actual term that we get is the sum of the L2 masses of each of these tubes. So what I'm gonna do now with a picture is show you how we go from that sum to the number of bad tubes and good tubes. So in this sum, you're adding over all the possible tubes that you may have. So you're gonna split them into 2 groups, the good tubes and the bad tubes. That's how you split your sum. For the bad tubes, you don't do anything. You just do Cauchy-Schwarz, and this is why the number of bad tubes is coming up. But for the good tubes, you get a logarithmic gain using Egorev's theorem. So let me explain what the idea behind that is with a picture. So if you isolate a single tube, the L2 mass on that tube is going to be controlled by the total L2 mass. So this is our tube for us. And what the Egorev's theorem allows you to do is to flow out this tube for time 1. And what happens now is that if you know that when you flew it out, it didn't come back to the original tube, it didn't look back, then the mass of this new thing combined that you got is twice the original mass that you had. And of course, you can keep flowing this picture as long as the Egorev's theorem allows you to do. You can go all the way up to, well, you can only use logarithmic times. And that's what you do. The mass of a single beam, you're going to control it by the total L2 mass now divided by log lambda. And this is why you can get this log lambda improvement from the masses of the good tubes. So this is what you do with the entire family of tubes that is good. All of them, you flow them out and they are going to give you this logarithmic improvement. So before moving on, I wanted to make a bunch of comments about the results in this slide. The first one is that this result that we have here has no assumptions. It's always true. All you need to do is to be able to have this decomposition in beams. The second one is that for this one, the assumptions that you have is that you have to be able to split the family of tubes that depart from X. So it's really a local statement in the sense that it only depends on how things are going to depart from X. Of course, you're going to keep track of the tubes for a long time. So these tubes are going to move along the manifold and they are going to cover a big part of it. But the only thing that you care about is it's the tubes that left from X. The other comment that I have is that we didn't use parametrics to do this. So we are getting these quantitative improvements of logarithmic type for the specific slide. but without using parametrics. So what I mean by this is that usually when you see a logarithmic improvement on any estimate, usually what happens is that the people behind those estimates are working under the geometric assumption that your manifold have negative curvature, non-positive curvature, and also flow, or more generally, no conjugate points. And what this allows you to do is to lift your computations to the universal cover, where you can use Hadamard's parametrics to control the wave kernel for logarithmic times. And the ability to have a parametrics for long times is what allows you to get these improvements in those setups. Now, in our work, we didn't have to build parametrics for long times. We are just using these tubes and we are keeping track of how they behave. What else do I want to say? Oh, something that's important is that our results, they hold in more generality that I'm stating. For example, you can here have, if instead of logarithmic times, you work, I'm writing on the slide, you work with times t lambda. And for the sake of this discussion, let's think that t lambda is polynomial times, okay? And suppose that you have a version of Egorov's theorem that will work for polynomial times, then what this will allow you to do is to get a polynomial improvement on your estimates. Another comment that I have is that this theorem, it's also more general in the sense that you don't have to split your tubes just in two groups, the good and the bad ones. Actually, what we did allows you to split your family of tubes into a collection of families, each of them non-looping for different times. And then the upper bound on this quantity is going to be given in terms of those non-looping times. What else do I want to say? Oh, also these results, they not only work for eigenfunctions, they also work for quasimodes of the operators. When working with quasimodes, you need to add here another term. And not only for eigenfunctions and quasimodes of the Laplacian, but they also work for eigenfunctions and quasimodes of pseudo-differential operators. They have to be elliptic and self-adjoint. What changes if you do that is that instead of using the geodesic flow to create your tubes, you have to use the Hamiltonian flow generated by the principal symbol of your operator. So instead of having geodesic tubes, you are going to have bicharacteristic tubes. And finally, before I move on to the next slide, what I wanted to say is that these results that I'm presenting you here about L-infinity norms, or rather the set of techniques that allow us to get these results, actually allowed us to get results on averages of eigenfunctions over submanifolds, LP norms, as I'm going to present, Bell laws. So these techniques are quite flexible. That's the point that I wanted to make before I move on. So now I'm going to give you a geometric setup in which one can actually build this family of good and bad tubes and actually get logarithmic improvements on your result, on the L-infinity mass at a point. So improvements on subnorms. This is the bound that I was stating at the very beginning. This is the universal bound, and you can improve on this bound. You have the work of Zog, Zeldich, Toff. That what they did was to first assume that if you fix a point x, the set of looping directions at x had to have measure 0, and then they could get a little low improvement here. Then they relaxed this to asking that the set of recurrent directions had to have measure 0, and then they can also get a little lower. Also, there is the work of my collaborator, Jeff Galkowski, where what he did was to reproduce all these results using the effect measures. And I want to point this out because this was the work that kickstarted all these articles that we've been producing since then about geodesic tubes. So the idea, what Jeff did was to use the effect measures to control how eigenfunctions, to understand how the behavior of eigenfunctions in phase space was affecting the behavior of the eigenfunction at a point downstairs on the manifold. Now, what we wanted to do was to get quantitative improvements, and if you're using the effect measures, you can only hope for little low here. So instead of keeping track of how the functions were behaving in phase space using the effect measures, we created this approximation by geodesic beams, and now we are keeping track of these tubes, and they allow us to get quantitative improvements as long as we can keep track of them for times that we can control. If one wants quantitative improvements, there are already results. There are, in this really nice paper from '77, he proved that you can get a square root log lambda improvement on the L infinity norm under the assumption that you have no conjugate points. So he is using Hadamard's parametrics to keep track of the wave kernel for logarithmic times to get this result. And what we wanted to do was to get the same improvement, but under a much weaker assumption. We didn't want to work with no conjugate points. And in order to explain how our assumption is weaker than this, I need to start talking about what no conjugate points means. So having no conjugate points on a manifold, what it means is that for any pair of points x and y that you may choose, and any geodesic joining the 2 points, and any Jacobi field along the geodesic that you may choose, what will happen is that if you force your Jacobi field to vanish at x, then the Jacobi field should not vanish when you get all the way up to y. So if you're not used to working with Jacobi fields, what they do is they keep track of how geodesics are spreading apart from each other. So what they are doing is they are measuring how, if you start with a geodesic that's starting in the direction of your Jacobi field, it's gonna tell you when you get all the way down to y, whether the geodesics spread apart or not. The fact that the Jacobi field at y is different from 0, it's telling you that the geodesic is spreading apart. And having no conjugate points, what it means is, again, that for any pair of points, any geodesic joining them, and any direction in which you may build a Jacobi field that vanishes at x, you must have that geodesics are going to be spreading in that direction once you get all the way up to y. In the opposite picture, what you have is a sphere where every point is self-conjugate, not just self-conjugate, but actually maximally self-conjugate. So let me explain that. On the sphere, if you start at the North Pole, no matter which direction you pick, it's gonna give you a closed geodesic that comes back to the point. So if you're working, say, in the n-dimensional sphere, you have n-1 dimensions that can give you Jacobi fields that vanish at the beginning. And in each of those directions, the Jacobi field, after you return to the point, it's gonna vanish as well. So what this means is that there is no possible direction in which geodesics are spreading apart. And this is what's called being maximally self-conjugate. And exactly this condition is what's saturating this bound. If you step away from this condition, then you can get improvements. So let me talk about that now. We are gonna, for a second, let's assume that we have here our point x and that it's not maximally self-conjugate. So what I mean is that if you return to the point x, then not all the Jacobi fields are gonna vanish once you return. So what this means again is that you have one direction in which geodesics are spreading apart. If you work under this condition, then instead of a big O here, you can improve it to a little O. If you want quantitative improvements, though, you just asking for something to not be maximally self-conjugate won't be enough. You need to have some quantitative control in your assumptions. And what we are going to do is to ask the point to not be uniformly maximally self-conjugate. So what this means is that if after time t, I return near the point x, how near? Exponentially close. So the radius of this ball is like e to the minus constant times t. If I return exponentially close to my point, then not all the Jacobi fields should vanish in the piece of the geodesic that enter that ball. So just so you have a good picture of what this means is that after logarithmic times, we are asking that if you enter a ball of radius 1 over lambda, then your Jacobi field shouldn't vanish, which is basically asking to not be maximally self-conjugate. And under this assumption, we can get the square root log lambda improvement. So if your point X is not maximally self-conjugate in this uniform way, then we can get the square root log lambda improvement on the value of the function at the point. Again, this is not a global condition on the manifold. This only depends on what happens with the geodesics that leave the point X. And we only get information about the value of the function at the point X. Which is a departure from the previous examples. This is the first time that we can get quantitative improvements, only depending on the point. And again, we don't use parametrics to do this. Okay. Before I move to LP norms, what I wanted to say, I didn't put this in the slides because I thought the talk would be too long, is that this assumption is what allows you to build good tubes and bad tubes. The fact that you're going to have one direction in which geodesics are spreading apart is going to allow you to have a big chunk of good tubes that are not returning for logarithmic times. Yeah, so I invite you to check out the paper on L-infinity norms if you want to know how that's done, or you can ask me after the talk and I can show you the slide that I erased. For LP norms, as I was saying, we have SOX bound. SOX bound, what it says is that the LP norm of an eigenfunction is controlled by lambda to the delta of p. Delta of p is just a function of both n and p, actually. And what's true is that so what happens is that the shape that this function takes, if you're above the critical exponent, is exactly this that I'm showing. So the critical exponent is this value here, and there have been improvements on this due to Hassel and Tacey in non-positive curvature. They get a square root log lambda improvement as long as you stay above the critical exponent. Now, if you are below the critical exponent, there are results. You have SOX bounds actually that work when p is between 2 and the critical exponent. And you also have quantitative improvements of logarithmic type on these bounds. But I don't want to get into that because our techniques cannot deal with these cases, at least not yet. What we can prove is the following. We can get a logarithmic improvement on SOX upper bound if we ask the following. So we are going to look at LP norms over a subset U of your manifold. And what we are asking is that for any pair of points X and Y in U, the point X should not be uniformly maximally conjugate to Y. So what that means again is that if you have X here and Y here, there should be one direction in which geodesics, they are spreading apart when you get all the way up to Y. And under this assumption, we get this logarithmic improvement, which in particular, it recovers Hassel and Tacey's result because this assumption works when you have no conjugate points. But also what I wanted to mention is that this is, again, a local result. This only depends on what happens with the dynamics with respect to the set U. You are not paying attention to what happens on the rest of the manifold to begin with. You only are concerned with what happens with geodesics that are shared by points between X and points X, Y in U. Of course, these geodesics may leave the set U when you're keeping track of them, but those are the only ones that you care about. And my goal for the talk was to explain to you how is it that one can use this geodesic beam techniques and this rationale of splitting tubes into good tubes and bad tubes to control LP norms. And so what I'm going to do next is I'm going to state the result in terms of good tubes and bad tubes that allows you to get this logarithmic improvement. And for the rest of the talk, what I'm going to do is I'm going to give you a sketch of the proof of that result. So here is the theorem. The theorem says the following. So you are gonna, I'm gonna go over the hypothesis in a second. Let me just show you first the result. The result says that you can control the LP norm on a subset U, and you can get the logarithmic gain as long as this term that we have here behaves like an error term. So let me explain what this term is. We can prove that there exists an n that only depends on the p, on the choice of p that you made, such that you get logarithm of lambda to the power of that n. And here what you have is this is the maximum number of tubes that you can have that are shared by any 2 points in U in times less than log lambda. And this again is just the radius of your tube to the power of n minus 1. So you can think of this term as the maximum volume that you can get for masses of bad tubes shared between any 2 points in U. What the assumptions are is that if you have any 2 points, so this is x here, and this is y, what we are going to do is we are going to look at the tubes over x, and you have to be able to split them into good tubes and bad tubes with respect to y. So the green tubes again are the good ones, the orange ones are the bad ones, and good simply means that all these green tubes are not going to reach your point y in times less than log lambda. These orange tubes, they do reach it in times less than log lambda, so those are your bad tubes. So for each pair of points, you have this decomposition between good and bad tubes. And if you can do this, then one can get this result. So again, my plan for the rest of the talk is to give you the sketch of the proof of how one deals with LP norms. And I'm gonna do this here in this blank page. What we are gonna do is to control the LP norms using the estimate that I was talking about that we proved with Jeff about the value of a function at a point x. So remember that I was saying that you can control the value of your eigenfunction at the point x by controlling the L2 masses of the beams that are leaving x. So just so that we are all in the same page, remember that these beams, we were building them by starting at the point x, looking at the co-sphere fiber at x, covering this sphere with balls of radius r lambda like lambda to the minus a half. And then you propagate these balls for a very short time, creating these tubes, TJs. And now you localize your function to each of these tubes, and then you work with your function as a superposition of these beams. Now, this L infinity bound here, as I was saying at the very beginning, it's saturated by the zonal harmonics. Remember the zonal harmonics, they were blowing up at the north and south pole, and the height of this blow up was like lambda to the n minus 1 over 2, saturating Hormander's bound. And the property that they have then is that the rest of this estimate actually becomes a constant when you work with the zonal harmonic at the North Pole. So let me record this for you so that you have a good picture of what's going to happen. Each of these beams for the zonal harmonic has L2 mass that's like r to the n minus 1 over 2. So all of them have this roughly the same mass, and then and again it's all of them. So the number of tubes that have this mass is like r to the 1 minus n, like that. So of course when you combine these two things into here, you are saturating the bound. Now, the way in which we are going to use this result on controlling the value of the function at the point x to get anything about LP norms is to, oh, you can no longer see me, right?
Indeed.
But we know you're at the Palace Hotel.
Here, right? Can you see me now?
No.
You cannot see what
Yeah,
I'm
yeah,
writing
we
now.
see now.
You
Can
can.
we see the presentation?
Are you good?
Yeah,
Can you see
we
or
can see
not?
now. Yes.
Yeah. Good. So what we are gonna do is to use interpolation to actually make use of the fact that we can control the L infinity norm. And so let me record this for you here. We just are to control the LP norm of a function on a set V, we are simply interpolating between L infinity and LPC. Now the thing is, the L infinity bit we can control using this result, but the LPC part, we cannot do anything about it. So in order to control it, we are gonna use Soul's bound. So that's this piece here. And what everything ends up boiling down to is to controlling the L infinity norms and the L2 norms over very small sets. So let me continue explaining what we do. First of all, without loss of generality, we are going to assume that we can decompose our function into this superposition of beams. On U. It may be that U is big enough and very big, and you cannot really do this in all of U, and in such case, you chop U into pieces and you can deal with that. So for now, just let me assume that U is small enough where you can have this decomposition. And now, once you have this decomposition, what you need to do is to make use of what this estimate is all about. So what this estimate is doing is controlling the function at the point X by using tubes, and not just tubes, but also the L2 masses of each of your geodesic beams. So what you're gonna do is you're gonna first cover U using balls. These balls are gonna be centered at points in U, and they will have radius R. And what this picture is supposed to be is that on top of these three walls, I'm just drawing the tubes that are running over them in phase space. So these tubes that you are seeing here are the tubes that if you project them down to the manifold, they would intersect the ball that they are on top of. And now the first thing that you're gonna do is classify these tubes according to their L2 masses. You're gonna filter them by their L2 masses. So to explain that, I'm gonna fix a K, and then what I'm gonna do is I'm only gonna look at tubes whose L2 mass is like 2 to the minus K. Okay, so well, I go ahead and I just, over the entire collection of tubes running over U, I only look at those tubes whose L2 mass is like 2 to the minus K. So say here I have these 3 tubes and so on. The next step is that what you want to do is to filter the balls that you created, these balls of radius R of lambda, by the number of tubes of mass 2 to the minus K that run over them. So for example, this ball has 2 tubes, this ball has 2 tubes, this ball has 3 tubes. So these 2 balls I'm gonna put together, and this one I'm gonna put in a different collection. So now what we are gonna do is we are gonna use an extra index in order to filter by number of tubes of mass 2 to the minus K over a point, and that index is gonna be M. So what we are gonna do is we are gonna filter by 2 to the M. This is the number of tubes over a ball. So in this picture, for example, let me pick M equals 1. Then what happens is that the balls that you're working with are gonna be this one and this one, because those are the balls with only 2 tubes over them. So now what you did was to filter all your tubes first by L2 mass, and then filter all your balls by the number of tubes that have that given L2 mass that you fixed to begin with. What this allows you to do is to work, instead of working with the entire LP norm, you are now gonna work with a bound for the LP norm in terms of these families of tubes and balls that you created. So
sorry, Yaiza,
yeah.
you keep only the power of 2, or it's a simplification for the presentation? I mean, 2 power m is, so if you have three tubes, it's not counted anywhere because it's not of the form 2 power m?
No, 2 to the m.
Okay.
And it's not a simplification. We really do the argument like this.
Okay.
So let me explain what everything that I just added to the slide is. So now here, we are going to consider the LP norm of this particular collection of tubes, which I'm going to say what they are in a second, over a union of balls. So for the picture that we have right now, the union of balls that I'm going to fix K. That means that I'm only looking at these tubes. And after I fix M, I'm only looking at these 2 balls. So this IKM is just the collection of balls that have exactly 2 to the m tubes of mass 2 to the minus k over them. And so for this picture, this union is just these 2 green balls. So let me write that down so that I can record it for you. So these are the balls with 2 to the m tubes of mass 2 to the minus k over them. And so this is just this is the set of such balls, which in the picture again, it's only these 2. What this set AKM is simply the collection of tubes of mass 2 to the minus k that run over the balls, the green balls. So in this picture, it would be this one, that one, and that one. That's what IKM is. So if you want, just for recording, these are the tubes of mass 2 to the minus k over a ball in IKM. The fact that you can control the LP norm by these sums, it's straightforward. So I'm not gonna comment on that. It's just manipulation of sums and balls. But what everything boils down to now is to try to understand what happens with the piece of the function that only has these tubes of mass 2 to the minus k that is running over these balls that have 2 to the m tubes over them. So we filtered the problem as much as we could. And let me now move this away so that I have more room to write things down. So now what's left for us to do is to split the tubes into 2 groups, the groups of good tubes and the ones for bad tubes. So I have my entire collection, you fixed K and M, and now you have the entire collection of tubes, and you're gonna split them into 2 groups. You want to work with good tubes, as I was saying before, and bad tubes. We were using orange for them. And the way in which you do this is as follows. So if, like in my picture, you only have 2 balls, then this is simply the assumption that we were given for those 2 balls. So remember I was saying that given 2 points, what you are doing is you're splitting the points leaving X into good tubes and bad tubes, where bad meant that they would reach the second ball in time log lambda, less than log lambda. This is the, and this is how you would split your tubes if you only had 2 balls. The thing is now, if you have 3 balls, then you have to be careful when you add the 3rd ball. That's what I'm doing right now in the picture. Because that 3rd ball is gonna have tubes interacting with the 2 prior balls. So for example, this 3rd ball is gonna have a bunch of it's gonna have a bunch of good tubes with respect to the 2nd ball, but this tube now is bad. And it may have other bad tubes with respect to the 2nd ball, and it may have bad tubes with respect to the 1st ball. but also keep in mind that perhaps one of the tubes that you have at the very beginning that you were considering to be good, it may now reach the third board that you add in time less than log lambda. And if that happens, Jeff, my collaborator, would say, now you're sad because you had to get rid of it. So you now turn this ball into a bad one. And this is how you would build the set of good tubes and bad tubes using our hypothesis when you have 3 balls. And now you just continue this process. So now we are approaching the end. What you do now that you split everything into good tubes and bad tubes is to control the pieces of your eigenfunctions that you are looking into. And what you want to do is to control the L-infinity norms and the L2 norms. So let me now stop for a sec and guide you through what we do. So you wanted to control the LP norms of this part of the eigenfunction, but you split the set of tubes into good tubes and bad tubes. So now you want to control these 4 sums, some of them for the L-infinity norm and some of them for the L2 norm, because remember, using interpolation, we are using the L-infinity and the L2 norm to control our LP norms. And now the idea is that if what you want to do is to control the L-infinity norms, what you will use for both L-infinity estimates is our bound on the value of the function at a point x, because we have filtered everything at this point. We have a lot of control on how many tubes of which mass are going through each ball, so we can actually control these 2 terms using our estimate. For the L2 masses, for example, for this term, that's the term that's going to give you the logarithmic improvement, because that's the term that has the good tubes in them. And using Agorev's theorem, you can propagate them, as I explained before, and get a logarithmic gain. This L2 mass here, we just control with the number of tubes. So you'll have something like the number of tubes to the power of 1/2 times the mass of each of these tubes to the minus k. And here is where the most delicate part of the argument comes into the picture. We somehow need to control the number of bad tubes. And the way in which we control it is by this simple estimate where we say, okay, the number of bad tubes that I'm gonna have, I can bound it simply saying, okay, the maximum number of tubes shared by any 2 balls in my set U is this BU that I defined in my theorem. So the BU was the maximum number of tubes shared by any 2 balls in my set U. And then if that's the maximum number of tubes that can be shared by any 2 points, then I can bound this the number of bad tubes by that BU times the number of balls squared. So this BU was appearing in the estimate for the error term. And what the delicate part of the argument is in effectively bounding IKM. So what happens is that now the rest of the argument consists of 2 things. It boils down to finding an effective bound for IKM and also adding in K and M and making sure that all the estimates that you got here on the right-hand side add up correctly. The argument for controlling the size of IKM is quite delicate, since the goal is to bound the number of balls with a given number of tubes running over them that have a given L2 mass. And the biggest difficulty in doing so comes from the fact that these balls may be arbitrarily close to each other. These balls have radius r lambda is going to 0. So you are trying to understand how L2 mass is shared by 2 balls that are super close. So in this regime, a single tube may touch several balls at the same time. We deal with this problem by developing a second by developing a second microlocal calculus. And I'm gonna keep commenting further on this. I can explain more after the talk if you're interested. But now what I'm gonna say is one can control the size of this set. One can control the number of balls of a given mass. One can control the number of balls with a given number of tubes of a given mass over them in an effective way. Now, when adding in K and M, it turns out that the indices that contribute to the upper bound, to this upper bound, the ones that you cannot get rid of, are the ones that keep the pieces of your function phi lambda that look like a zonal harmonic. That is, the K's that matter when you are actually studying this upper bound that you got are those for which the beams have the same mass as the zonal harmonic. So this is what the 2 to the minus K is gonna look like. And the M's that matter are those for which the number of tubes over a ball are the same as those for the spherical harmonic. So this index M are those so that 2 to the M is like R to the 1 minus M. So all in all, the values of indices K and M that really matter when you're computing this sum, for those values, what happens is that this set IKM turns out to be bounded. What this means is that the number of points in U at which the function can look like a zonal and hence saturates the upper bound is finite. So you can at most have finitely many points or balls that behave like the North Pole for a zonal harmonic. And that's the idea when you are dealing with LP norms for P bigger than P critical. And that's the end of the sketch of the proof. And that's the end of the presentation. So thank you very much.
Thank you very much, Yaiza, for this very nice talk.